Arroyo is a cloud-first SQL-native stream processing framework developed to try to address some of the things that have been difficult about previous generations of stream processing technology. I talked to Micah Wylde today, who's one of the founders of Arroyo, the framework, and the company, about the framework, kind of what got him into it. And at a few points, we got to dig down pretty deeply into some of the really interesting parts of stream processing. Let's listen in. Hello and welcome to another episode of the Real-Time Analytics Podcast. I am your host, Tim Berglund, and I'm joined today by Micah Wylde. Micah is the CEO and co-founder of a company called Arroyo. Micah, welcome to the show.
Thanks for having me.
You got it. Tell us first, what is Arroyo? And I'll ask you, we'll go from there.
Yeah, so Arroyo is a new-ish, I guess now, stream processing engine that lets you write SQL queries on top of streaming data, for example, in Kafka or another data stream. You can think of it as really a modern reimplementation of Apache Flink. My background is running Flink, developing Flink applications, leading teams built around Flink. And Arroyo really came out of my frustration of many years trying to make Flink work inside of large organizations, and especially with kind of non-technical or not streaming expert users. So people like product engineers and data scientists. I saw at several companies just how challenging it was for those people to be successful on their own building Flink applications. And I thought there was a lot that we could do kind of at that core engine layer to make it possible for those folks to be successful with streaming, without a ton of support from streaming experts. So Arroyo is really an attempt to build that experience focused on really excellent SQL support. So people don't need to learn kind of a new language or framework to build correct, reliable, fast streaming pipelines. And then also a lot of improvements to the operational experience so that it's much easier to run without needing a lot of tuning and special casing for every application. It's written in Rust and takes a lot of the kind of learnings about stream processing from the research community over the past decade to kind of advance the state of the art a little bit beyond kind of what Flink is doing.
I love that. And here on the Real-Time Analytics Podcast, Flink is a friend. It's funny, just earlier today, interviewed a person who's, I'll say, a key player in the Flink community. However, maybe I should say, and what you said about data scientists, people who aren't stream processing experts successfully building applications in Flink, I think I got to give that one to you because it is the kind of thing where you have to put yourself into the world of stream processing. That is what you do if you are building applications on Flink, and if things are supposed to be abstracted away, those are probably pretty leaky abstractions, and that's funny. I don't know that Flink itself is troubled by that. That's just kind of how it is, and you from that community said there's got to be a way to make this easier. Tell me about the things. I would love to dig into how Arroyo works and just some other questions about your perspective on real-time SQL and choices you've made, as an experienced builder in this space. What were the things that you saw? You said you were frustrated. Was it just, gee, this is too hard, or were there other things that were structural and, clearly to be motivated to go rewrite it in Rust, fun as that sounds, things had to be bad in your perspective. What were those things? What were the struggles?
Yeah, so before starting Arroyo, I spent 5 years leading the stream processing teams at Splunk, and before that at Lyft. So working on problems with a lot of data, and where, especially at Lyft, being good at real time was pretty core to the company. Every product feature pretty much had some degree of real time aspect to it, and the core experience of hailing a car and having it arrive, and then making sure that you get to your destination safely at every stage of that process, there is real-time data feeding into that. When we um, figure out how long it's going to take every car to get to where you are by looking at real-time traffic data, by estimating the price to kind of balance supply and demand in the marketplace, doing real-time safety checks. So, seeing if the car is like speeding or doing things that seem unsafe or going in the wrong direction.
Oh, okay. I don't know why I'm surprised, but yes, those would be things that you would do.
Yeah. So there were dozens of Flink pipelines that kind of lay underneath all of these features. And the structure there was we had a core streaming team that we had a bunch of Flink committers. We did core development on Flink. We built tooling around it, libraries, infrastructure, Kubernetes operator.
Mm-hmm. As one does.
Yeah. And like this made the experience a lot easier because, you're not just being thrown at Flink, you're given a lot of like structure and tooling. But still what we saw was that out of our I think we probably worked with like 50 plus engineers on various product teams and data engineering teams and data science teams. And I would say like out of those, maybe like one or two engineers really became like self-sufficient over that time. So every one of these kind of features that we wanted to build, whether it was like a new ML feature or a new product feature that relied on real-time data, it was always done like with deep consultation of the streaming team from basically the start, like describing like how you might lay out these pipelines through the development, and then especially like once it was going into production or testing, like doing the debugging and the optimization and the tuning in order to allow it to actually like run reliably at lift scale.
And those one or two engineers that became self-sufficient, they were either application engineers or building some kind of data pipeline that to you modeled as an application. They're users, and you're an infrastructure provider.
Right.
And so of the, I'm going to guess hundreds, there was a less than 1%.
Yeah.
Okay.
Right.
Okay.
And really, we always wanted a model where like we are a service provider. We're AWS. We're providing, some high level service, and users can just come and use that and express their like specific domain problems and, basically be self-sufficient on top of that platform. That was always the dream. And we never were able to get anywhere close to that.
It's a good dream, Micah. I don't know that anyone could or should hold that against you. Dang it. Yeah.
And then at Splunk, a good chunk of my team kind of moved there, and we built V2 of that platform, and we tried the same thing. In this case, building it specifically for Splunk's end customers, which is an even harder market, you can imagine, when it's basically anyone who wants to use Splunk, all the like tens of thousands of users, and we want to allow them to be successful building real-time data pipelines.
Oh, okay.
And that, again, proved like way too high of a bar for Flink. You
had Micah on the edge from Lyft, and now in this environment.
Yeah. So it's really, and then that's like the user perspective. And then as an operator, as the person like responsible for these pipelines running, I had a whole other set of frustrations due to being woken up in the middle of the night many, many times due to Flink issues. And those issues were, there's a few classes of them, but the biggest class is really dealing with state. And I think that's the core operational challenge with all of these systems. But
I was going to bring it up if you didn't. So yes.
The thing is particularly challenging. You have to, if you have a lot of state in your pipeline, some of our pipelines had hundreds of gigabytes or terabytes of state. Every single operation on your pipelines involves checkpointing all that state to S3. And then when you want to like rescale it or recover from failures or update your code, you have to spin up a bunch of infrastructure, download all that state, and restart your pipeline. And this can take minutes to hours with Flink. And that means you really cannot automate any of this stuff. You have to, all of these operations are like database migrations, basically. You have to do it extremely carefully with a lot of attention.
At that scale, that was not tenable. Okay, so those were some of the challenges, and this led you, and by all means, fill in blanks in the story here. I'm not trying to fast forward you, but this got you to
Yeah, so it was really like looking at these years of working with Flink, trying to solve these problems inside of Flink, struggling to make progress in the project itself, and just running against limitations of like architectural decisions that were made a long time ago. And I don't want to throw any shade on Flink here. Flink is an amazing project. I deeply respect and I'm friends with people who have worked on it and continue to work on it. But ultimately, it's a project that came out originally in 2012. So there's just a lot of things that have changed in how we deploy our applications, how kind of our computers work. And then we've just learned a lot about this set of problems in that time. And Flink has a lot of these assumptions baked into it that are really hard to evolve at this point.
Yeah, no, definitely the case that an application that sort of grew up with the assumption that there would be a data center that it was deployed to, and some chef or puppet or something, turning the dials, and in the contemporary environment, there can be some mismatches in, their architectural decisions that I think unwittingly could have relied on those assumptions, and now in a containerized and substantially more automated, I'll just say more cloud native world, those might not match.
Yeah, if you run on a Kubernetes cluster that's provided by like your company's infrastructure team, they're going to assume that workloads are like pretty transient. It can be moved easily. Like they want to, maybe roll every server every week so that they're able to keep up with their update cadence. And if you have a Flink application, that is a really bad mismatch because Flink expects to run on the same set of hardware forever, essentially.
Yeah, okay.
It was designed for that world where we had like servers that were in a data center and were dedicated to a particular task.
Yes.
It's been, an awkward, fit to kind of push it into this like Kubernetes world where like things are constantly moving around and it's expected that all your infrastructure is like pretty elastic.
Yeah. Yeah. So, tell us about Arroyo.
Yeah.
And I'd love to know a little bit about how it works, and in particular, what are the architectural choices that you made, coming from these things that didn't feel good. Tell us about Arroyo.
Yeah. So Arroyo really was like a kind of clean room design based on like many years of working on Flink and with Flink. So it's heavily Flink inspired, but kind of also takes inspiration from a lot of the research that's been done in the past decade in the stream processing space. So at a high level kind of architectural look, it's pretty similar to Flink. We still take pipelines and represent them as a distributed data flow graph. So however you start up your pipeline, whether it's SQL or another language, eventually that ends up in this kind of directed acyclic graph of computation where every node is some operator that does some potentially stateful operation, like a join or a filter or a window. And the edges are kind of the events flowing between those operators. These operators can be parallelized. So you can have multiple parallel subtasks that handle some shard of your data. And the framework is able to shuffle the data so the correct events end up on each shard according to their key. And then there's a checkpointing algorithm, which in Arroyo is quite similar to the Flink one, that is able to consistently snapshot all of the state in this graph. So you're able to save it to typically S3 and restore it on failure or rescale or whatever. So that stuff is all basically the same. The things where we've really kind of moved past or making different technical decisions than Flink. The first one was to really start with SQL. So in Flink, SQL was really bolted on to an existing Java, or originally Scala API. And in Flink, SQL is just kind of translated into that Java API. So in practice, you really have to understand kind of what's happening at that lower level in order to be successful with Flink SQL at any kind of level of complexity.
That abstraction is leaky, and you need to know that one layer down. Okay.
So
I was going to say, to be fair, in 2012, this was still the time when we were somewhat petulantly saying we didn't need SQL anymore. So you got to give them that. And Scala,
Absolutely.
And the industry was young and needed the money.
I was myself kind of a latecomer to SQL. I faced years of users coming to me and asking for SQL. And we didn't really support it at Lyft or at Splunk. And I was like, you should just write Java. It's so much easier to just express this as a Java pipeline.
Yes.
But when you tell that to data scientists,
a person who knows Java real well.
Right. Yeah. When you tell that to data scientists, you do not convince them that they should just write this in Java.
No. And the whole that whole episode has certain developmental analogies. That 2010 to 2012 was all of us kind of being 16 years old and thinking dad is real stupid. And a small number of years later, all of a sudden, dad's less stupid,
Yeah.
So
yeah, I was around for some of that. The heyday of MapReduce.
Yeah, and me too. It's fine.
Yeah.
And I had no excuse, but we were all there. So you're saying, back to Arroyo, you're taking a SQL first approach and not a Scala API first approach.
Right. So the goal is that, like, if you know SQL and you're used to writing kind of like batch analytical SQL queries on Snowflake or BigQuery or whatever, you should be able to directly port that experience into a streaming system like Arroyo. You shouldn't have to learn a bunch of quirks about like how Arroyo thinks about SQL and like, what constraints are placed on that by the underlying Java API or whatever. So that was really like where we started, is like, how do we do these complex analytical SQL stuff? Like, how do we do that really well and unsurprisingly for SQL experts?
Okay.
And that led to a very different kind of internal design than Flink. So at Flink, you have very like strict kind of architectural layers. At the core layer is like the kind of core data flow API that's built on top of a series of kind of like state APIs that are very abstracted from like the actual state storage. And that has nice properties. It means you can swap out the state storage layer pretty easily. Application developers that are targeting those stateful layers don't need to really think that much about like how this actually works. But you also leave a lot of kind of performance on the table for those like higher layers. And similarly, when you're translating kind of SQL queries into the Java layer, you're kind of limited on what is expressed there. So we took the other approach, which is like we optimize for individual SQL features, like all the way down to the state layer. Okay. So we don't have these kind of like layers of abstraction that you have in Flink. It's you're kind of able, when we're implementing, window joins or whatever, or doing specific SQL optimizations like top K, we're able to like represent that in the most efficient way at the state layer because we don't kind of have all of these layers of abstractions.
Got it. So you can get more with less, compute wise.
Yeah, exactly. So that's part of it. Another part of it is how we think about state and how we store it and manage it. And this started from a rule that like we have to be able to checkpoint every 10 seconds at whatever size of state. And we have to be able to restore pipelines. So do the checkpointing restoration process within 30 seconds for every size of state.
I like that constraint.
And these are somewhat arbitrary numbers, but like the idea is that if you can hit numbers like roughly like that, then you don't have to treat your operations around these pipelines as these like gingerly handled like database migration-y things. You can basically just throw this in a Kubernetes operator that is able to do kind of like stateless microservice style operations around scaling and recovery and migration, and assume that the framework can handle it. So it's really about like how do we enable people to just automate these kind of like routine operations without needing to put so much care into it. Okay.
That is adapting really in the operator. The complexity finds its way into the operator, adapting this is on a sheet metal box in a data center whose address I know to this is an image in the managed Kubernetes I've randomly selected today.
Yeah, exactly. And so it's really like, making it work more like a stateless microservice and less like a big heavy database.
Okay, not trivial. That.
Not trivial, yeah.
Yeah.
And that's something that we're still kind of evolving on. We took one approach originally based around using a key value store as our state backend, and that's worked out okay. Now we're in our kind of main open source release. We're using kind of a Parquet files state backend
Okay.
based on Parquet files that we're able to pretty efficiently stream to S3 at very high scales. We're still working on kind of like how do we restore this really quickly for like terabytes size states, but for tens of gigabytes to hundreds of gigabytes, this works pretty well, and we're able to typically hit that like 30-second
Okay.
kind of goal.
If that 30-second constraint also had to develop a certain upper bound on the size of the state, I wouldn't feel like you were bad at what you do. I'm not a customer. I'm just one guy with a podcast, but that seems reasonable. I mean, there's going to be a point at which,
so the next
bytes, moving the
I
bits.
can tell you what we're working on there, which is the kind of next level here is what we call external state, which means, okay, so you have, let's say, if you have that much state, you're probably dealing with a lot of historical data.
Yeah.
So maybe you have like a month-long window. And the access patterns there, let's say we're doing anti-fraud, which is a space I spent a lot of time in. The kind of way these pipelines look is you have users coming in, doing transactions, doing, browsing around your website, producing click events or whatever. You want to build up a user history. So for every user, you want to track like how many events did they have in the last 5 minutes, the last hour, the last 30 days, for over a bunch of like different dimensions. And then when a transaction comes in, you basically need to look up all of that data and use that to produce ML features that are going to go into a risk model. But for most of the time, the users aren't making transactions. We don't actually need that full user's history. So you can actually store it externally. And people who build these kind of applications by hand will typically, structure it that way. They'll have some kind of data store that they store these user histories in, and then they load them in as needed. It's really hard to like build these things correctly when you're doing it kind of in an ad hoc way like that. So people would like to be able to use these stream processing engines, but they're not that good at like figuring out what data is needed at given points and like how you can store it. So solving that problem automatically is really like, I think that's the kind of big solution to this problem.
Tiered storage is kind of what you're talking about, right?
Yeah. So tiered storage is that comes from like kind of the like Kafka world or kind of the more traditional database world.
Yeah,
where it's
and we do that in StarTree's fully managed Apache Pinot implementation. We'll put some of your data in S3 in a super smart way. It's not this naive load the whole pile over there and go download it, but it's this kind of neat way of doing it, but respecting that idea that there's old stuff and taking a hit on latency is okay there, and there's fresh stuff, and there's kind of analogous to a lot of things we do in the physical world.
Yeah.
I have a desk drawer, and then there are warehouses, and there are boxes in my garage and places in between. But is that not exactly what you're talking about?
Yeah. So, I mean, these are like similar sets of solutions in like different domains. I think in the kind of stream processing world, this is a really hard problem that is less obvious how you would solve it than in like the database world. And no one has quite cracked this. I'll call it Rising Wave is doing like really interesting stuff in this space.
Okay.
But no one else is really, I think, working on this exact problem. The challenge is that you can't go to S3 for every request. When you're doing millions of requests per second, you need to be very clever about how you structure the data across the different tiers, what data you cache, how you cache it, how you pipeline the events that you're processing while still maintaining like the ordering semantics that you need. So yeah, it's
all
a
very hard problems there.
hard problems, but yeah, that's kind of the goal is um, how do we minimize the data that actually needs to be local to the processing nodes um, in order to enable you to treat these processing nodes as like transient and kind of more stateless services.
Deep dive on something that I think is just relative to the level that we're talking. It feels like it's 4 levels down. We're maybe just following things I'm paying attention to right now. But you mentioned checkpointing and watermarks, or rather checkpointing, which is, if I understood you correctly, adopting the Flink approach and not the watermarking approach of, say, a Kafka Streams. And I don't know among the various solutions offhand who does what. It seems like watermarking is unique to Kafka Streams, or almost. You might know better than I do, and dig into that a little bit. Again, it's super far down relative to everything else, but it's an interesting choice, and I just love to hear your thoughts.
Yeah, so there's a few kind of intertangled things here. And in Flink, and Arroyo, we also have something we call watermarks, but I think it is a little bit different than what Kafka Streams means by that.
Okay.
And it's not quite connected to the checkpointing, or sort of loosely. So just an overview of checkpointing, which I'll call snapshotting. Both Flink and Arroyo use an algorithm that's based on something called Chandy-Lamport. It's like from the 80s, from Leslie Lamport, who's like
Leslie Lamport,
yeah, super, like just has done everything in distributed systems even before we knew we needed it.
It's why we have them. Thank you, Dr. Lamport.
Yeah. Plus LaTeX, just out of left field there.
Oh, that was also him.
Yeah.
Okay. Yeah, he's bored one day and he's like, my papers look lame.
Yeah, exactly.
I'll fix that.
But yeah, so the basic idea is we have this distributed data flow that I was talking about earlier, these stateful operators connected by these event streams. And we want to be able to produce a consistent snapshot of this entire graph. So we want to have like a point in event time, essentially, or it's not logical time, where we can say for every operator, an event has either been seen or not seen. And we want to capture the state at that kind of point in time. It's not a literal point in time, because like different operators will see different events, at different times. But it's kind of this logical notion that like every operator in the pipeline has either seen or not seen each event. And Chandy-Lamport basically lets us do that. It's a very clever idea. I think it's probably too low level for this conversation, but if you're interested,
however, we'll have a link in the show notes.
Yeah. And basically once you have that capability, you're able to take this checkpoint, shut down, and restart. And so long as you're reading off of like sources that have, a like notion of ordering and the ability to rewind, so something like Kafka with its offsets, then you're able to basically continue processing from exactly where you left off with no repeated or duplicated events or dropped events. So it's a very powerful capability of systems like Flink and Arroyo. Watermarks, at least in Arroyo and Flink, are about gauging some notion of completeness for the data. So a watermark is like an estimation of basically have we seen all the events from before a certain time. So if we say our watermark is a minute ago, then we assume we've seen all the data, previous to a minute ago, and we're able to
that timestamp.
Yeah, exactly.
Yeah.
So we're able to, for example, close windows that finished more than a minute ago. And this turns out to be really crucial for a lot of stream processing applications to kind of trade off between latency and completeness.
Right.
So obviously, you can wait forever and you'll have all the data, but it's not that useful in a stream processing application. You need at some point to decide you've received enough data to kind of like compute your results and move forward with it. And watermarks are a way for the user to kind of specify whether they'd like lower latency or more complete data.
There you go. And you never, there's there's always a time at which data will be arriving late and you're simply going to refuse to process it.
There's different strategies for that as well.
Yeah.
You can obviously just drop it. You can maybe reprocess it and update your results. Or you can do something more complicated. The Flink Java API, there's a lot of options, and you can also implement kind of your own handling of that.
Yeah. I guess it'd be depending upon the properties of the operation happening. If it was a properties of that function, maybe you can update it, maybe you can't. And but in any case, I guess you've got a couple of things working there. One, the value of the data, this being real-time data, is assumed to get smaller as time goes on. It's super interesting right now, and the more and more time passes, the less that event asserts about the state of affairs out in the world, and so no big deal. And number two, you need infinite storage to actually do that, and you're not allowed to have infinite storage. It's just, this whole thing would be easier, but you can't have it. So
yeah, and like the core idea of the watermark, which originally is from Google Dataflow, the Dataflow paper, is that like there's no one answer to this. It's really application dependent. So, you may have like data that's coming in from sensors, and it's really important that you are processing it within, a second in order to take some action on that. If your factory is about to blow up, like you can't wait for every single sensor to report its data. Like you just need to like operate within some time bound there.
Yeah.
Whereas if you're doing something financial, and you need to like really make sure you have all the data, you're going to want a much like longer bound on that. And you're willing to accept more latency. So it's really like a user level decision about this trade-off.
Right, which is fair. Given what you're trying to accomplish at Arroyo and kind of the motivators that have come in, you've brought into this. How do you know when you've succeeded? What does an accomplished mission look like?
Yeah, well, I mean, the big version of this is like no one is using Snowflake anymore. Like everything is real time, and that's just kind of the default approach is to use stream processing systems for these whole classes of daily, hourly batch jobs that people build today. And the stream processing systems are able to, specifically Arroyo, hopefully, are able to kind of allow people to choose any point on this spectrum of like completeness and latency while providing excellent performance and really good reliability and cost effectiveness. Because ultimately, batch processing is a special case of stream processing where we just like wait a day to process it. So like stream processing is able to do that incrementally and kind of choose anywhere on that spectrum. So that's like the big version of this. The smaller version of this is we really just want to enable people who have real-time applications who are scared off from deploying stuff like Flink today. We want them to not be scared to choose real-time for where it like really makes sense and there's a business value there. Because I talk to so many teams who are like, a PM who's like, yeah, I have all these ideas for these real-time data sources we'd like to get into the app, but like my engineers are like, we can't do that. We can't deploy Flink. It's too much work. It's too scary. So we want to just like stop those conversations and just say like, if you think you can like do this in Bash, then you can also do it in real time.
My guest today has been Micah Wylde. Micah, thanks for being a part of the Real Time Analytics podcast.
Thanks so much for having me. And if you're interested in Arroyo, it's open source on GitHub. Check it out. There's an easy Docker container you can just run and play with it.
And there you have it. If you feel compelled to help us spread the word and grow the real-time analytics community, you can give us a rating on Spotify or Apple Podcasts or wherever fine podcasts are sold. If you're watching us on YouTube, hey, subscribe and, of course, hit that notification bell. And you can always share your favorite episodes on LinkedIn or Twitter or wherever it is you do social media. Thanks, and I look forward to talking to you in the next episode.